This is the first of a set of videos on first order modelling. This video focuses on mass damper systems. We're going to assume that students have been through the introductory videos on modelling, so that was things like parallel springs, parallel pipes and so on. And therefore that students understand that there are often simple analogies between apparently very different systems. However, the earlier videos focused on steady-state behaviour, and now what we want to do is look at systems where the behaviour is dynamic. Things are changing. We're going to begin by looking at simple mechanical mass damper systems. Here's an example then of a mass damper. Now this schematic is meant to represent something like a car. So this big mass here could be considered to be the car. This force would be the engine force, and these hashed lines down here are meant to represent friction. There's something which is trying to slow the car down. So there's a simple model. So we've got a drive force from the engine, we've got friction, perhaps from the wind and perhaps from the road, and the car has some mass. What we want to do is say, how do we model this simple scenario? Well, first, we remind students of the parallel arrangement that was covered in the earlier videos when we looked at springs. If you have mechanical components arranged in parallel, which means components share the same velocity and the force is divided among them, you can use this little diagram. You'll see there's a force here, F, and then that force is divided into two different parts, one which goes through component 1 and another which goes through component 2. And in this particular case, we're going to view that component 1 could be the mass and component 2 will be the friction or the drag. Now in this case, the next question is to ask, well, what sort of equations will represent the movement of the mass and what sort of equations will represent the friction? So here we have it. If we're looking at friction, we've got an equation a bit like this. The force is some constant times the velocity. And what about mass? We have Newton's law, which says the force is mass times acceleration. Let's put all this together again. So here we go. We're going to repeat what we've got here. Now for component 1, here I'm going to make it clear this is the friction term. And component 2, this is going to be the mass term. So we've got an applied force F, which is split into two components, F1 and F2. We've got a velocity V, which these components are moving, and we're going to say what equations represent these two components. So you'll see we've got force F1 tackling friction, so the equation is F1 equals BV. We've got force F2 accelerating the mass, so we've got F2 equals m dv dt, and then we've got force balance, which says F equals F1 plus F2. So if we put these together, we end up with F equals m dv dt plus PV. So there we go. This form of mass damper gives a simple first order differential equation. You've got the force applied F, and that gives you mass times acceleration plus some constant times velocity. So the motion of a car, simplistically with a fixed engine force, is governed by a simple first order differential equation. Now there are other types of mass damper. In this particular case, the friction that we were looking at was independent of location, because it was based maybe on the roughness of the road and wind and things like that, but it wasn't based on a particular physical component like a spring or a piece of mass. Similarly, the acceleration component was also independent of location. It was dv dt. It doesn't matter exactly where the car is located. However, in practice with mechanical systems, a lot of the physical components are actually fixed. They're fixed to something like a wall or a floor. And we want to ask ourselves, will this have an impact on how we model those systems? And in particular, we also want to say, do there exist some physical components which are equivalent to a damping or a friction and how might we model those? So the friction we did with the car's just rolling along the road, but there could be some component which has an equivalent sort of equation where F equals some constant times velocity, and that's what we're going to look at next. So here's some easy examples. Imagine something like a bicycle pump. The faster you pump it, the harder it is to move, and therefore the equation of a pump is, roughly speaking, the same as a damping. So what I'm going to do here is I'm going to imagine that one end of this damper is got a fixed point here, so that's a bit like a wall. So one end is fixed to wall, the other end is moving with velocity v, and I apply a force F. So if I have this type of damper fixed at one end, a force applied F, then the equation I'm going to get is F equals BV for an appropriate B. So that's in a damper with one fixed point and one end free. What happens, however, if I have both ends free? So now it's implicit I've got the same force at both ends from continuity. This end might be moving with velocity v, and the left-hand end might be moving with velocity w. So in this case, the sort of equation you're going to get is F equals B v minus w. So the friction force from this damper is actually dependent on the relative velocity of the two ends. And so you'll notice there's two different types of damper here. Are both ends free or just one end free? And that affects how we include them in a model. Some things for the students to think about then. Before we model a mechanical system, we need to be very careful to look at the particular physical build. And we need to ask ourselves things like, is the same force going through several components? If it is, we've probably got a series arrangement. And if you look back on the videos on springs, you'll see the impact of that. So, have we got a series arrangement? If there's a series arrangement, then the displacements or the velocities tend to add, and the overall impedance goes down. Alternatively, is the force divided between various components? So we're using force balance. And, here's the critical thing, do those components share the same displacement or velocity? In that case, we maybe have a parallel arrangement. And then when you add components in parallel, the impedance tends to get bigger. And we want to ask ourselves, with these mass damper systems, have we got a series arrangement? Have we got a parallel arrangement? Or perhaps, have we got neither? Here's a simple example then of what would be a parallel arrangement. You'll see I've essentially put a wall here so the damper is fixed at one end. Now the reason I've done that is so that I can write the damper is moving with velocity v, the mass is moving with velocity v. You can see both the mass and the damper have the same velocity, which is one of the things we wanted for this parallel arrangement. We've also got this force balance. The force is divided between them both. Now in this case, you'll see I can model the damper, F1 equals BV, the mass, F2 equals m dv dt, force balance, F equals F1 plus F2, and therefore I get F equals m dv dt plus BV. And you'll notice this is actually the same equation as I got for the car earlier. So if I have this arrangement where one end of the damper is fixed and the other end is free, and the free end is basically connected in parallel with a floating mass, then we have a simple first order model which represents the behaviour. Okay, here's another arrangement. Is this arrangement parallel or not? Okay, you'll see that again the force has been split between the mass and the damper. So I've got F equals F1 plus F2. You'll see that the mass moves with velocity v and one end of the damper moves with velocity v. However, the other end of the damper moves with velocity w, so the damper's now got two free ends. And this means the damper equation is this one down here, F1 equals b v minus w. So when I put all this together, I get F equals m dv dt plus b v minus w. And I look at that and I say I'm a bit stuck, because I've got this w in this equation. It's not a simple model, and the analysis is not as easy as the previous slide. And you might be glad to know we're not going to talk about this anymore. It's beyond the remit of these videos, except that students recognise that they've got a situation which is more complicated. What about this arrangement then? In this particular case, I've now put two mechanical components in series, and you'll see that they share the same force. So that was one of the ways we could recognise a series arrangement. The same force was going through all the components, but they have independent displacements. So for example, I could have the mass moving with velocity w, and that's one end of the damper, and the other end of the damper moving with velocity v. Now, if I look at the damper equation, you'll see that I've got force equals b v minus w. So I'm looking at the relative velocity of the two ends, which is v minus w. I look at the mass, and that's Newton's law, F equals m dw dt. And you look at those two and you might say, well, what do I do now? It's not quite clear how I solve these. Well, there's a little trick here. I'm just going to do this briefly because it's not central. I'm going to differentiate the first equation. There it is. Where I had F equals b v minus w, I'm going to differentiate everything and get df dt equals b dv dt minus dw dt. And then what I can do is I can take the dw dt from here and put it in here. So if I write that, you're going to end up with df dt equals b dv dt minus b, and now I need dw dt, which is f over m. Now I'm not going to talk about that one anymore, because you can see straight away this again is a non-simple expression and therefore beyond the remit of these videos. What about this one then? This looks at first sight like it might be a series arrangement. You look at it mechanically and say, well, the mass and the damper seem to be arranged in series. However, this is a trick, and this is a warning for students. Always be very careful when you're sketching mechanical systems to think precisely about what is happening. So if I add on displacements, put displacement of the mass v and here velocity of the damper, what do you notice? The two velocities are the same. They are not independent. The next thing you might like to ask yourself, well, let's look at the forces. And you notice the force on one side of the mass is F, on the other side is F1. So in fact, the force F is being distributed between the mass and the damper. And so this, although it might not look like it at first sight, is a parallel arrangement. And if you look at the two equations at the bottom, F1 equals BV for the damper, F minus F1 equals m dv dt for the mass, then what do you get? F equals m dv dt plus bv, and this is the same equation as the ones we got earlier for a simple parallel arrangement. So something that looks different may in fact be equivalent to a parallel arrangement and give you a simple first order model. So in summary, we've illustrated the model derivation for simple mass damper systems that arise with simple friction and a simple mass, and we've shown that you get a first order model of this form, F equals m dv dt plus bv. However, we've also shown that you've got to be very careful with mechanical components, especially with things like masses and dampers, to check, is the arrangement parallel? Is the arrangement series, or indeed is it neither of these? And it may not be obvious without a careful analysis of forces and velocities exactly what you're dealing with. These more complex cases are beyond the remit of these videos, and you'll find we don't really discuss it in the videos that follow this one.